Hello everyone, I am Chetan Rajoria from the Department of Mechanical Engineering and I welcome you all in this new online session. In this session, we are going to discuss about Varignon's theorem and its statement and proof. So let's proceed. So what is the exact statement of Varignon's theorem? According to this theorem, which is also called the principle of moments, in a coplanar force system, the algebraic sum of the moments of all the forces about a point is equal to the moment of the resultant of those forces about the same point. Means, suppose there are three forces in a coplanar force system. There are three forces, and there will be a resultant of those forces. Suppose that resultant is R, and the forces are F1, F2, and F3. Now, let us suppose we take the moment of all these forces about a point. Let us suppose that the point is O. So the moment of these forces are, say, M1, M2, and M3. Now, let's add up these moments algebraically according to their directions, clockwise or anti-clockwise. It may be positive or negative. So the summation of these moments is, say, M1 plus M2 plus M3. So the sum of the moments of these three forces, which is M1 plus M2 plus M3, will be equal to the moment of the resultant of those forces R multiplied by T, means the moment of the resultant and the distance of the line of action of the resultant from the same point. The point from which we are taking the moment of other three forces, the moment of other three forces. So how to prove the statement? For this, we'll use some geometrical methods. So let's draw a diagram for solving, or you can say for proving this statement. This is the y-axis and this is the x-axis. Okay. Let us suppose the forces are F1 and F2. For simplicity, we are taking only two forces. So the forces are F1 and F2. This is the first force, F1, and this is the second force, F2. First of all, we will find the resultant of these two forces. Now, how to find the resultant geometrically? We will use the principle of parallelogram law. Okay, the parallelogram law of forces principle. For this, we will draw a line parallel to this force F2, and we will start from this point. So let's draw a line parallel to the second force like this. Similarly, we will draw another line from this point, and the line will be parallel to the first force F1. Now, what will be the resultant of these two forces? The resultant is represented by this diagonal, and let us suppose that its resultant is R. So these are the forces F1 and F2, and the resultant is R. Now we will choose a point about which we will take the moment of these forces. For simplicity, we will choose the point on the y-axis. Okay, so let us suppose that the point is this, M. Okay, this is the point about which we are going to take the moment of all these forces, means the components F1 and F2, as well as the moment of the resultant. Now, for taking moment, we need the minimum distance of the line of action of the force from the point, means the perpendicular distance, the minimum distance. And for finding out the minimum distance, we will drop the perpendiculars from this point on each and every force. Okay, So let's show the perpendiculars. This is the perpendicular dropped on the line of action of the first force. Let us suppose the joining point of this perpendicular is N. Similarly, let's draw the perpendicular on the second force F2. So this is the point at which the perpendicular meets to the line of action of this force F2. And suppose this point is M. So M has already been taken. So let's take this point as T. And let's draw the last perpendicular on the line of action of the resultant of these two forces, that is on R. Let us suppose this point is S. Okay, so the perpendiculars are meeting at these points N, T, and S on the forces F1, F2, and R respectively. Now let's consider that the inclination of these forces F1 and F2 from the horizontal line are respectively θ1, θ2, and θ. So let's show these angles. This is the angle made by the first force with the horizontal line, and this angle is θ1. The angle made by the second force with the horizontal line, that is from the x-axis, is θ2. And the angle made by the resultant from the horizontal line is theta, only theta angle. So this angle is theta. Now, please consider this angle. Clearly, this angle is θ2. So what will be the remaining angle? Because F2 is making θ2 with horizontal, means from the x-axis. So what will be the angle made by F2 from the vertical axis, that is from the y-axis? The remaining angle will be 90 minus θ2. So clearly this complete angle between F2 and y-axis is 90 minus θ2. Now consider this triangle. Suppose this is the origin O. Consider this triangle OMT. Okay, please consider a triangle OMT. So this complete angle MOT, this angle is 90 minus θ2. Therefore, this angle becomes θ2, because we already know that this angle is theta, because these are the perpendiculars. Because therefore, 90 minus θ2, 90, and this angle becomes θ2. Similarly, please consider this angle. The angle made by the first force F1 with horizontal is θ1, already marked here. Therefore, what will be the angle made by the force F1 with the vertical axis, that is from the y-axis? The angle will be 90 minus θ1. So clearly the angle between y-axis and F1 is 90 minus θ1. Okay. Now please consider this triangle MON. Triangle MON. This is once again a right angled triangle in which this angle is 90 degree. Now this angle is 90. This angle is 90 minus θ1. Therefore, this angle becomes θ1. Okay. Similarly, we can prove that this angle becomes theta. Because when we consider this angle theta here, the angle made by the resultant with the horizontal, this angle is theta. Therefore, the angle of this resultant with y-axis becomes 90 minus theta. And when we consider triangle MOS, in the triangle MOS, this angle is 90 degree. This is 90 minus theta. Therefore, this angle becomes theta. So in this way, we have calculated the inclination of the perpendiculars from the y-axis. And these angles are theta 1, theta 2, and theta respectively. Now, using these angles and these triangles, we are going to prove this statement. So first of all, we will find out the moment of each and every force. Okay, what we are going to follow the procedure. First of all, we will calculate the moment of each and every force F1 and F2, and we will mark those moments as M1 and M2. Then algebraically, we will add these two moments and we will show that summation as M1 plus M2. And in the last, we will show that the summation of M1 and M2 will be equal to R into the perpendicular distance of R from the point M. So let's proceed. First of all, we will calculate the moment of the first force, F1. We will write it as M1. M1 is equal to F1 multiplied by, suppose this length is D1, okay? We are assuming that Mn is equal to D1, Mt is equal to D2, and Ms is equal to D. Okay, these are the length of each and every perpendicular. So M1 is equal to F1 multiplied by Mn. That is F1 multiplied by D1. So this is the value of the first moment. Now, let's find out the moment of the second force. And let's write this moment as M2. M2 is equal to F2 multiplied by Mt. Force multiplied by the perpendicular distance. Okay. So F2 multiplied by Mt. What is Mt? D2. So this is the moment of the second force. Now, let's sum up these two moments. What is M1 plus M2? M1 plus M2 will be equal to F1 into D1 plus F2 into D2. Now, please consider these triangles one by one. We will consider the triangles MOT and MNO. Okay, these two triangles. D1 is what? MN. Now, MN can be written in terms of MO. Please consider the triangle MON once again. This right angle triangle. This angle is theta 1. Okay. And this is D1, the length of MN. Therefore, we can write MN in terms of MO because MO becomes the hypotenuse of this triangle. Okay. So it can be written as F1 multiplied by MO cos theta because this becomes the resolved part of this hypotenuse. Okay. The resolved part with the angle. Therefore, this becomes cos theta. So we can write D1 as MO cos theta, theta 1. MO cos theta 1. Similarly, we can replace the value of D2 as MO cos theta 2. How? Once again, please observe this triangle MOT. This is once again a right angle triangle, and MT can be written in terms of MO because the angle between MO and MT is theta 2, marked here. Okay, so it can be written as D2 can be written as MO cos theta 2. Now in this expression, clearly MO is common. It becomes F1 cos theta 1 plus F2 cos theta 2. Now please observe this bracket part, F1 cos theta 1 plus F2 cos theta 2. What is this? This is clearly indicating the summation of the horizontal component of these two forces. This is the horizontal component of the first force, F1 cos theta 1. This is the horizontal component of the second force, F2 cos theta 2. And we are adding up these two components. This will provide you the horizontal component of the resultant of these two forces. Okay? The resultant of these two forces, F1 and F2, is R. Therefore, F1 cos theta 1 and F2 cos theta 2, the summation of these two can be written as R cos theta. Okay? So let's replace this bracket with R cos theta. So this becomes M1 plus M2 is equal to MO into R cos theta. Okay, the summation of the horizontal components of these forces becomes the horizontal component of their resultant. Now this can also be written in this way, R into MO cos theta. Fine. Now what is MO cos theta? Look at the diagram once again. MO cos theta. Please observe this triangle MOS. Triangle MOS. This is once again a right angle triangle. So what is MO cos theta? Because this angle is theta. This becomes MS. Okay. And what is MS? MS is D. So let's replace R into D. So we can conclude M1 plus M2 is equal to R into D. So this is the final resultant. Or you can say the final expression which we are going to prove here in this complete procedure. M1 plus M2 is what? The summation of the moments of individual forces is equal to the moment of the resultant of those forces about the same point. In this procedure, we have taken the point as M, about which we have taken the moment of all these forces. So in this way, it has been proved.